And this year, he's going to tell us how to build digital currencies, make an ICO, and become billionaires by the end of this year, right? Anything like that going to be as
like
part of your presentation?
Yeah, it's possible.
Okay. Let's welcome Peter with a big round of applause. Thank you.
Okay. So today I'll be talking about building a digital currency. A little bit of it will be about economics. Some of it is about some of the technical decisions that we made that might be of interest to you. And last but not least is how it can be customized using Java code. So we'll get to look at some actual code. A little bit about me. I'm a Java champion. I've been in IT for well over 25 years. I've been the CEO of a small company for 5 years, specializing in custom execution engines for tier 1 and 2 banks. Also very active on Stack Overflow. I have over 13,000 answers, which is the most for Java or the JVM. So our background, and my background, is in building custom execution engines for major banks, in particular redeveloping trading systems. And this is the expertise I'm looking to bring into the blockchain space. A lot of our software is open source, so we get significant number of downloads for our open source products. 2 of them have over 1,000 stars, and in total we've had over 1 million downloads. So we get good community size. So today I'll be looking initially at the economics around a digital currency, which is perhaps a surprising topic, but it's fairly essential in any digital currency to think about the economics of how is it going to work. And in some ways, a lot of the questions that come up are the sorts of questions that central banks normally answer. But as a developer, you may need to come across these and think about how you're going to cover these issues. I'm going to look at some of the existing solutions that are out there from my point of view as to where I see their strengths and weaknesses. A solution that we have, which is open source, where we've architected for performance, because one of the weaknesses of many of the existing solutions is scalability. And last but not least is how can a blockchain be easily extended using some Java code to add new transaction types. So in terms of economics, Bitcoin has a model where everything is mined. So all of the coins tokens that are created have been mined or will be mined. The reward for mining halves roughly every 4 years, and it will eventually run out, and there'll be no more reward after the year 2140. However, the intent is that over time, the value of the fees will be more significant than the reward, and that over time, the real revenue raiser, the real incentive to run these Bitcoin servers is to get the fees. And it's already the case that the fees are a good percentage of the reward. Last time I checked, it was about half. So within 4 to 8 years, the fees may actually be larger than the reward. So the fact that it's declining over time isn't so important. Ethereum also has a declining fee structure, but it's not without limit. So while it is declining, it won't completely run out, which means that the number of Ethereum isn't capped. But the fact that it's not capped, to me, doesn't seem to be too much of an issue. It's not a large concern, partly because the reward gets smaller and smaller over time. It doesn't disappear as such, but it's not significant. It's not going to create too much inflation. IOTA, by comparison, has all of the coins created up front. So every possible coin is already created right from the start. which means there's no reward for miners. There's no opportunity for miners to make money. Instead, the only way to make money is to hold the coin itself and hope that it will go up in value. The number of coins is higher, but that's because their units are different. And they do it from what is the minimum divisible unit. And in reality, they do largely talk about everything in terms of millions of this unit. And it ends up being much the same as Bitcoin. So the fact that there's about 1 million times more coins doesn't really matter, because in reality, everyone generally talks about M iota, which is millions of iota anyway. Ripple have a slightly different structure. They, again, everything is determined in advance, all the possible coins. Instead, they retain 60% of the coins, which is quite high for a coin solution. So the company itself that created it, they keep 60% of the coins in reserve. They're not actively used at the moment. However, they have the option to release them in the future. So it's a bit like having a flexible cap, but it can only be this extra 60% they ever release. There's no, I haven't seen any material about them saying that they intend to release or on what basis they might release in the future. So there's a little bit of uncertainty there as to, what point will this happen. But nevertheless, again, is a coin where all of the value is known in advance, the possible values. So in our solution, we've tried to come up with something that's very similar to that, in that a lot of the coins are reserved. However, the reserve has a particular purpose, which is to minimize volatility. So there's often the term used called a stable coin, and a stable coin is linked to a fiat currency. So you might have a stable coin that's linked to the American dollar, for example, and the exchange rate is always known, usually 1-to-1. That works in terms of stability, but doesn't always work in terms of being economic for the solution to run it. So what we're doing is having something that's not quite that stable, but something that's more stable than the very volatile currencies you see today. So on our exchanges, because we have our own exchange that's written into the code, we allow a certain amount of floating, but also have an AI that actively attempts to minimize volatility whenever it exceeds some threshold. So that's either through selling off or buying back. And so for that reason, a large percentage of the coins are reserved for a sell-off if the price goes up, and that will build up a reserve so that it can buy back if it goes down again. However, in the software that's there, there's not necessarily even because it's an open source platform, if you were to use it, you could use it the way you wish. Whether you want to have fees, whether you want to have an additional coin of your own or not, that's entirely up to the implementer. So moving on to the architecture, some of the architectural decisions, and in particular, how do other systems perform? Something of a benchmark is the Visa payment system. Now, Visa can handle around 24,000 messages per second. I've seen different numbers in different publications, but that seems to be sort of the median number. And the number they actually get is a fraction of that, but it's still a sizable fraction, about 1,700 transactions per second sustained over the day. So they may get peaks of 24,000, but the sustained is lower, which is what you would expect. Now that to some degree is a benchmark, and in my opinion, if you've got a system that is only as fast as a Visa, you're not really a terribly compelling option from a performance point of view, because there is already a system that works and a lot of people use that does this. If you want to be compelling from a performance point of view, you need to be substantially more than this. as a threshold to say, yes, this is a compelling solution. In the future, Visa won't be able to do the job. You need to have something that can do X. So how do they compare? Well, Ethereum and Bitcoin currently do in the order of 3 to 7 transactions a second. So that's not really a lot compared to Visa. Ethereum has some plans to improve scalability. However, that's possibly a couple of years away, and the amount of improvement they're looking at may be 10 to 100 times. It's a bit unclear to me, at least, exactly how much improvement they will realistically get. Now, if you compare that to some of the other available solutions, you've got Ripple, Corda, which is also called R3, and Hyperledger. And these are all in the vicinity of somewhere between 500 and 1,500 transactions per second. And there are some other less well-known solutions that are in this sort of throughput range. But again, while this is substantially better than Bitcoin or Ethereum today, it's not better than Visa. This is close to what Visa actually gets, never mind what is theoretically possible. So from that perspective, it's better, but it's not a particularly strikingly, significantly improved throughput. So what sort of numbers do we get in our open source solution? Well, if you have a single box for each node, and each one has about 8 CPUs, so we're looking at a fairly modest server, not costing, it's high end, but it's not costing too much, and that's to run an i7 processor. We're getting around 52,000 a second sustained for a subchain. We can handle peaks higher than that, but the sustained rate is a little over 50,000 a second. So that's quite a significant improvement without necessarily a huge investment in hardware. Now, the main thing to note from this is for each subchain. So we can handle many subchains, so that you can scale even further by having more than one subchain. Another way we can scale is to put more hardware into each node in the cluster. So if you have a number of nodes working together, we've done tests where you get about 400,000 transactions per second for each subchain. So it's quite a lot more. The question in my mind is, would you ever need to go to this point? Largely because you can scale by having more subchains as well. So it's quite possible that this is starting to get into the scalability realms of you probably never really need this. So how do we go about doing this? We use what is sometimes called C-like Java. We have a C-like Java framework. This comes from our trading background. However, from my perspective, I actually think of it more like C++-like Java in the sense that it's still object-oriented. It works very naturally with normal Java, but it's very low level, very much focused on performance and avoiding any operation that creates garbage, for example, avoiding any operation that takes a significant amount of time. The actual sign and verify that the blockchain does is not written in C, it's actually written in assembly. And we're using a library that already exists, it's widely tested. One thing I would definitely recommend you not do is try and write your own cryptographic algorithm. Even if it is better in some way, it won't have had the same level of review as established algorithms. So you're much better off using an established one if you can. So we use ED 25519, which is an elliptic curve encryption, and it has a 256-bit implementation that's written in x64, so it's highly optimized, and you get very good latencies and throughputs compared to other 256-bit encryptions. So in fact, most of the CPU power is actually burnt in assembly code. So the fact that using Java isn't actually so important. Another thing we do is we very much look at how optimizing it for the hardware we have. So each function does as little as possible, very much focusing on what's the most efficient way to use the hardware. So this reduces power consumption, increases the potential throughput, but to some degree, keeping it super simple also makes it easier to debug. You're going through less layers, less transformations, less things going on in your application. So in terms of CPU power, so this is the high-end large node configuration where you're doing about 400,000 a second. So even in that scenario, about 40 CPUs are actually burnt just doing the signing and verifying. So it's very expensive, but it's not in Java at all. There's also, depending on the number of connections, and we're assuming a high number of connections, about 24 processors we estimate would be used just dealing with TCP, all the different TCP connections. And again, this is not in Java, this is in the OS. It's already written for you. And in that configuration, only 4 threads, 4 cores are actually spent doing it running in Java. All the rest is just Java telling the system what to do. So the fact that we've used Java isn't actually much of an overhead. And in fact, how we do things and how we use it is much more important than the choice of language. There are plenty of C++ solutions that not only use more power, but are significantly slower, not because it's written in C++, that C++ is slower, it's because of the algorithms they've used are much slower, fundamentally. Achieving consensus. So one of the things that we do, which is a little bit different, is that every node in the cluster in each round can create a block. So in most of the solutions, one node in a round successfully adds a block to the chain. So in proof of work, that's done on a competitive basis. In proof of stake, one node is nominated based on its stake to add a block to the chain. The downside of this is that you limit the amount of concurrency that goes on in your system. Whereas in our solution, every node can add a block to the chain simultaneously. So as you add more nodes, it doesn't necessarily get dramatically slower. In fact, it can speed up as a result. That's the ultimate goal in terms of scalability, is to get linear scalability, as do a lot of web services. They use linear scalability, add more web servers, you can handle more clients. That's the aim in any scalable solution. By comparison, in something like Bitcoin, it not only doesn't scale, it actually gets slower. So the time to consensus increases with log n of the number of nodes. So as you add more nodes, the whole thing gets slower and slower, apart from chewing up more power. So for example, Bitcoin at various times has consumed more power than Ireland, like the whole of Ireland. So it chews up more power than a decent-sized country. And it's written in C++. So whereas what we're doing is we're making it that the nodes can add, each of them can add a block in each round. So they can work much more concurrently with each other. And so when you come to consensus, you don't necessarily need as many nodes to run the solution. So it's another thing we do is we somewhat arbitrarily limit the number of nodes that can run any particular subchain. And that's to reduce the overhead of consensus. It's also working on the assumption that we assume that beyond a certain number of nodes, we're not necessarily adding any more redundancy or reliability. So we're looking at somewhere between, depending on how it's configured, somewhere between 5 and 200 nodes per subchain. So looking at this in terms of a diagram, to achieve consensus, it goes through 3 phases. First, in a round, every node creates a block concurrently. Then they replicate those blocks to each other. Then the next phase is they gossip about what blocks they've received from each other. So every node gossips about what they've got. Then, and the next phase is they then vote on which blocks should get included in the next round, based on all the gossip they've seen from all the other nodes. And then last but not least, as long as a majority of nodes vote to include the same blocks, you've achieved consensus at that point. And any one of the nodes at that point can announce that these blocks will be included in the next round. So it's not guaranteed to always succeed. Certainly in ideal cases, it always succeeds, but in non-ideal situations, it's not guaranteed to succeed. However, we make the rounds very short. So a subchain might have rounds as short as 5 to 10 milliseconds. So if it misses the occasional round, they can't get consensus, they can't agree on which blocks to include, they will probably achieve consensus in the next round or the one after that. And so you only get a very small delay when consensus can't be achieved in a round. So putting this in a bit more detail, so messages come in from the client on the left-hand side here. They go into a gateway. And when it comes to customizing, this is one of the components you would plug in. What does the gateway do for your custom message? Then it goes to the blockchain, and what that does is it starts combining transactions that are going to the blockchain into a block. Like it starts adding it to a block. So it adds it to its own block. So each node is creating its own block for that round. Then the gossiping engine, so it also replicates. So the gossiping engine then starts, after a short delay, starts announcing, these are all the blocks I've received and have copies of. Then the next stage is all of them vote on which ones should be included based on the gossip they've seen. And lastly, any one of the nodes, if it sees a majority, can announce that these rounds can be included. So once consensus has been achieved, the replayer then replays all of those blocks, all the transactions in those blocks in a consistent order, so that every node will also replay the same transactions in the same order. And that goes to the post-blockchain processor to make decisions about whether those transactions were successful or whether any outcomes from those transactions. And in particular, that is another piece where you would, if you're going to create a custom transaction, you would implement it and say, this is what this transaction does. Part of the reason that's included in this phase is that on a weekly basis or on a periodic basis, if you customized it, on a weekly basis, it will take a snapshot of the entire system. This has a number of purposes. One is that if you've got a very high transaction rate, you're going to build up a lot of transactions that are only ever going to get longer and longer as the years go by. So you want to be able to periodically checkpoint the system and be able to pick it up from a known point and just roll forward the transactions that happened after that checkpoint. And in fact, GDPR makes that more likely to be a requirement, because one of the requirements of GDPR is that you have a right to be forgotten. But if you've got transactions that have to live forever for the system to work, how do you achieve that? So for example, Bitcoin, every block has to be validated and played from the start for it to work. So then how do you get forgotten? Whereas if you're taking regular checkpoints, after a certain period of time, those checkpoints can be discarded, and you can just continue from any point, from any checkpoint, in fact, that you've retained. So everything can, after a certain point, can be implicitly discarded and the whole thing still runs. Now, one of the key things that I've seen come up again and again is that because there's a lot of enthusiasm for using blockchain, a lot of solutions would work equally well with just a distributed ledger. And in fact, a lot of solutions would work equally well with just a regular database. So, because pretty much any kind of database which is actively added to you could put a blockchain in front of it. But is there a technical merit in doing so? When is there a technical merit in doing so? Rather than being a commercial, hey, we're using blockchain, that sounds much more exciting. An example of this is there's a company in the US that called the Long Island Brewing Company. And not surprisingly, they made drinks. Now, they decided they would rename the company to the Long Blockchain Company. Their share price went up by a factor of 6. And then a few months later, the SEC decided to investigate them to see whether they really had anything to do with blockchain other than changing their name. And so it is useful as technologists to say, well, what point does blockchain actually add something it couldn't do with a normal database? And one of the key things about a blockchain over a distributed ledger is that a distributed ledger requires every node to be trusted. And certainly in a database, every node that's running that database also needs to be trusted. Right? So if you're root or sys, system administrator on that machine, you can do anything. And if it's distributed, you can do anything that will affect any other box as well. Right? So there's a high degree of trust required to add any node to the system. But say you're running a system that's across organizations, across companies, where the level of trust is harder to establish, or it's not even necessarily desirable. Well, this is where blockchain can actually help, because the level of trust required to add a node to that cluster is much lower. And it depends on the solution as to how low that is. But I guess one of the extreme examples is Bitcoin, where anyone, anywhere in the world, without even knowing who they are, can be added to the cluster, as long as they're running the software. They could be doing anything in any country, under any jurisdiction. There isn't actually any barrier to entry other than having internet and a suitable piece of hardware to run the software. So there's a much lower barrier of entry for participants to join a cluster. Now, realistically, in enterprises, people, they generally want to know who is joining a cluster. They want to know, they'll know something about the company. So that's not necessarily, it could be anonymous, that isn't necessarily a requirement. But in a commercial environment, they may not still, they may know who they are, that there's a certain basic understanding, but they may not know, for example, does this company comply with all of the security policies my company has? Does this company have all the same processes that I have? And given that they're a competitor, am I completely comfortable with everything they do? Right? That may not be the case, right? And or at least that can be a proposed reason why a particular company can't join a partnership, because say you've got 3 companies running a cluster and there's a 4th, then all those 3 companies have to be comfortable with that 4th company joining. As it gets larger and larger, as you get more and more companies, each company added needs to be comfortable with, all the existing companies have to be comfortable that new company can join, and they have to be comfortable with all their policies and how their systems run. Where if there's much lower barrier to entry, it's much easier to bring in a new partner or a new company to help run the service without a high checklist. So it's much more likely to happen. So there's an actual commercial benefit to running a cluster of blockchain nodes that you cannot achieve with a simple database or a distributed ledger. And it's really about the level of trust you need to have in the operators of each node. One of the benefits of having a lower level of trust, it means that if one of those nodes gets hacked, the impact it can have on the entire cluster is much lower. Obviously, you want to have all the standard security protections, but nevertheless, even if they are bypassed, the amount of damage that any one node can do is very limited, if next to nothing, because that doesn't give you access to the whole cluster. Even if you compromise a decent percentage, it still doesn't give you access to the cluster. So So one of the things that blockchain gives you is fraud protection, and that is that only the holder of a private key can generate a message which has the signature that matches the public key for that account. So you can authenticate who produced any given message. It also means that even the nodes in the cluster cannot generate messages on behalf of any user that they don't have the private key for. So they can copy a message, and they can distribute them, they can validate them, they can say what should happen if this is an accepted message, but they can't create ones of their own. And by not being able to create ones of their own, that takes away the ability for an individual node to defraud the rest of the cluster, even if it's compromised deliberately or otherwise. So one of the things you're trying to protect yourself against that a normal cluster, a lot of clusters, what you protect yourself against is that one of the nodes dies outright or just stops working outright. But what you can do with blockchain, you can make it Byzantine fault tolerant, where you can have individual nodes actively trying to bring the system down or to defraud the system. And you can protect yourself against that, which is a higher level of protection, which then means you've got a less requirement to trust what the behavior of that node is going to be. So as I mentioned earlier, we're very much optimizing for throughput in this kind of system, which is actually different to what we normally do. As a company, we usually optimize for latency over throughput. Generally speaking, for the applications we tend to work on, if you make the latencies low enough, you'll get the throughput you want. So you just focus on lowering the latencies. However, in the case of blockchain, one of the intrinsic features is having rounds. And those rounds take a certain amount of time. They add a certain amount of latency, which we've got some strategies for mitigating against, but really that creates a certain latency weight delay. Then there's the encryption, the signature and verify. The sign and verify adds a certain amount of delay as well on every message, which cannot be really optimized for by just throwing more CPUs at it, because it's not concurrent. So you've got some constraints as to how low the latencies you can make them. However, it is possible to optimize for increasing throughput by trying to make as much of the system run concurrently as possible and focus on optimizing the few pieces you can't make concurrent. So fortunately, most of the CPU, as I mentioned earlier, is concurrent. All the signing and verifying can be made concurrent between messages. Not within a message, but between messages. So if you've got 1,000 messages, they can all be signed or they can all be verified on different processes completely independently. So you get very good concurrency, even though that's the most expensive bit. The second most expensive bit is handling all the TCP connections. But again, every client can get their own thread, for example, as one approach. Although for scalability purposes, you may want to use NIO. But in any case, throwing CPU at the problem does help. You get very good scalability in those two areas. The two areas where you don't get good scalability is in consensus. And that's a fundamental nature of the problem, what you're trying to solve, which is getting them all to agree on something. You can only parallelize that so much, and so that is one area where you want to minimize the overhead. The other one is the actual transaction processing itself. The transaction processing is fundamentally ordered. Whether a transaction succeeds or not depends on whether previous transactions have succeeded or not. So can you transfer $100 out of your account? Well, it depends on whether enough money was transferred into it in the first place, or has all the money been transferred out of it yet? So the order in which transactions occur are very important, and as a result, that is one of the key serial pieces. And in fact, in our case, the 400,000 is determined by how fast it can run through the transactions after they've been serialized. And that's the defining bottleneck. The consensus, by comparison, even though it's an overhead, you can adjust how often the consensus happens. You can also limit the number of nodes involved in the consensus. So between those two, you can reduce its overhead. Whereas speeding up the transaction type, there's only so much you can do. As I mentioned earlier, we were looking at doing regular checkpoints, probably weekly. Some systems actually have daily checkpointing, which is potentially an option. And the reason for checkpointing is that you don't want to replay from the start. The reason this is a problem is in particular is if you want to have very large throughput. So with Bitcoin, one of the benefits is that you're limited to about 3 transactions a second. So even after running for 5 or so years, the number of transactions you have to replay from the very start is quite limited. Now, if you were to try and have a system that could handle, say, 10,000 times the number of transactions, you now have 10,000 times the number of transactions to roll forward to work out where you're up to at any one point. And you could actually get to the situation where nodes take almost, can never catch up, or have very great difficulty catching up. So for example, a Bitcoin node can join the network in about a day. But if you had 10,000 times as many transactions, 10,000 times 10,000 days is about 30 years. Right? So that would be 30 years to catch up with 5 years worth of transactions. So you've got a fundamental problem that you could end up with nodes that just never catch up, ever. Whereas if you're using checkpointing, it doesn't matter how many transactions have occurred before the start of the week or the start of wherever you're taking the checkpoint. You just need to load the state at that point, and then you can roll forward the transactions that happen from then. And as I mentioned, GDPR requires the ability to be forgotten, so you can't practically retain every message ever. You certainly can't design a system that is a requirement. Now, as I mentioned earlier, we can have multiple subchains. So there's a number of solutions that are looking at using subchains to speed up the network as a whole. So one of the things that Ethereum are looking at doing is having sharding. So you, by address, you arrange the accounts across multiple chains. And when 2 accounts are in different chains, you have a coordination problem, but only the 2 chains involved need to talk to each other. One of the problems with doing this is that if you use hashed sharding, which is what Ethereum does, or is planning to do, then any 2 accounts being in the same chain is just statistically random. And as you get more and more chains, it becomes increasingly unlikely. So you're always going to have coordination between chains. There's no inherent benefit in the strategy used. It's quite fair in the sense that any one person's account has an equal chance of being in any chain. However, that doesn't necessarily reflect how the systems are generally used. So the approach we're taking is that we're using the ISO 3166 standard, which defines 4,000 regions around the world. And that region code becomes part of your address. It's also used to determine what chain you're in. So if you're in Kluge and you're transacting with someone else's account who's also in Kluge, you're going to be in the same chain, always. If you're transacting with someone in Bucharest, it will depend on how far the chains have split. Quite likely, they will also be in the same chain. But if they split enough, they won't be. This gives you the advantage that, sorry, where possible, a large percentage of transactions will be local to a single subchain, and the inter-chain transactions and interaction is kept to a minimum, just by choosing the partitioning strategy. So I think I've mentioned that already. Instead of using hashing, we use something that fits the logical use case of the assumption is that most people will do transactions with around where they live or within the country they live. This doesn't mean that you can't hold an account in New York, for example. So you can have an address that's in New York, one that's in London, one that's in local to here. And you could transfer money between them, but then when you do transactions in those regions, they will be more efficient, and if there's a fee structure, it will have lower fees as well. So some examples. So in base, the region is encoded in base 32, or the entire address is encoded in base 32. So the first address is in the region US New York, and there's some random number after it, which makes it unique. And there's another, say another account, which in this case is in Victoria, Australia, which is where I'm from originally. And again, the rest of the address is just to make it unique. So initially, there'll be just one chain that'll cover the entire world. Then as the number of nodes goes up, it'll start being split. So this is a base 32-bit long. The very first bit then gets split in half. So half of the addresses go in one chain, half go in the other. After it splits 5 times, because it's base 32, after it splits 5 times, the very first character will determine which chain it's in. So this gives us somewhat arbitrary allocation that all the countries that start with U will be in the same chain. However, by the time it splits 10 times, which is split quite a lot, it will be localized to an individual country. And then further, split 15 times, you're starting to get not any country, but the first letter of the region code. So essentially, this is part of the way we can control the number of nodes running a subchain. As more and more nodes enter the system, the chain just starts splitting and becoming more localized to a particular region. So you switch from having global chains which need to have consensus around the world to a chain that might only need consensus in Romania. And therefore, you can get lower latencies between those nodes and better locality. So that's just what I mentioned. So what's a realistic upper limit on terms of throughput? In theory, with 4,000 chains and every one using highest spec, you're looking at about 1.6 billion transactions per second. Realistically, no one I know has come up with a use case for that. So that until there's actual use cases to drive that to happen, it won't happen. A slightly more realistic number is probably in the region of about 100 million transactions per second, where some of the clusters are not necessarily using the latest hardware. Not all the nodes, not all the subchains are fully split. Nevertheless, even 100,000 is way beyond most use cases. So one of the key issues that comes up after scalability is integration. How easy is it to integrate this solution with any other solution? And what protocol will dominate in the end? So from a banking point of view, the main protocol they use, which is used across multiple different use cases, is a fixed protocol. Now, fixed protocol is not particularly pleasant protocol. It's sort of text, but has control A's in it. The message type field is, of course, identified by the number 35. What else would you identify it? The first field has to be field 8, and the last one has to be field 10. It's got all sorts of features which are not really designed for friendliness, but nevertheless, it's probably the most widely used protocol. And for that reason, we're looking to have gateways that support the fixed protocol so that it can be integrated with existing systems. We're also looking to have the exchanges in the system will be AI managed. That AI will be an open source AI that's running across all the nodes in that chain. So there isn't like a separate system running the AI. Every one of the nodes in the cluster is running the AI as well. Between them, they make decisions about when to either sell off or buy back currency to stabilize the volatility. So a simple approach is to set a price at the start of the week, which is got a plus or minus 3% spread, and basically they will buy back or sell off when that threshold is reached. That's a very simple strategy, but you can get a lot more sophisticated than that. So in terms of roadmap, we have a working prototype now. We have a website which isn't very public, but you can have a look at potentially. But the main thing to look at would be the open source solution that's available. We're looking to, we actually sometimes get 500,000 messages a second. I'd like to make that much more consistent so we can quote that number. We're also looking to have like a test system, a test net that's actually up and running and available. We have one that's running, but it's not widely available. And we're looking at pre-OCO investment now. The other thing we're looking to do with the open source is to have a licensed extensions. So maybe your company would prefer to just have a once-off license for the product. Then we can do that, and then you don't need to pay on a per coin basis, which is how a lot of ICOs are actually funded. Because a more traditional model is we sell the software for licenses and sell the consulting around it. Nevertheless, the open source is Apache too, so you can get started with that at any time. So what does it look like to extend the platform? So this is under active development. We have a running platform, but it's only for the messages that we've written code for already. What we're looking to do is redevelop it so that it's easy to add custom message types and custom transactions. And what does that framework look like? At the moment, it's all written in Java, so obviously the extensions are in Java. The protocol itself could be written, could be implemented in any language. So we're not limiting ourselves to Java as such. So the three bits that you need to add if you're going to extend it is to create a DTO for the transaction type itself. So each transaction has a DTO associated with it, one or more. It might be a certain message comes in and a different message comes out. So that'll be 2 straight away. Then you need a component which says what happens when the client talks to the gateway with this message. What does it do? What sort of validation does it do? Does it reply immediately? What does it send onto the blockchain? And last but not least, what does the blockchain do once it's been approved and ordered? So just going back to this diagram, you've got DTOs coming in, you add a component to the gateway, you add a component to the blockchain processor, and then you've got a new transaction type. What does that look like? Well, it starts with an interface for each protocol. You can have a number of protocols. Each protocol has its own interface, and in this case, it only has one message type, which is the Hello World example. This is what the DTOs look like. That's our usual DTO sort of structure, where most of the code, apart from the setters and getters, most of the code, all the interesting code is all handled in an abstract class. So all the serialization, deserialization is all handled there. So this is an example of a gateway. So in this case, the gateway, this is where after the client sends the message, this is the first component to be hit before it goes to the blockchain. So in the first case, it validates the message and says, well, does the text have anything in it for my Hello World example? If not, send back a command failed event to the client and say, hey, that's not going to work. Otherwise, pass it on to the blockchain. So then this is what gets called, after it's successfully gone through the blockchain, what happens. So again, there's the hello example. And in this case, you don't send it straight to the interface. You actually say where you want that message to go. So in this case, the message goes to the destination that was specified in the original text message, and it has the original message sent. So that original message also has the source. So what does that look like? Well, to create a text message, you just call the constructor. The toString is generated for you, which turns the message into YAML. The YAML has the advantage that it's not only relatively easy to read, but also can be always deserialized back into the original object. So if you ever log out a DTO, you can always just copy-paste that into a test example, and no information is lost, because you can download it, decode it. So in this case, I'm just showing that when you deserialize it, you get the message back that you did originally. Oops. I'm going the wrong way. So this is a more complicated test. Now, you might be wondering, why have we structured our components the way we have? The reason we've done that is we want to be able to test the components with no framework involved. So I'm very keen that when you create a complex framework or run something that runs up as a service, that you can actually test the business logic without the framework being involved, without adding any complexity or threads or doing things or making your test run take longer. So in this case, you can actually see that at the very top, I create 3 mocks. These are the outputs, where the outputs are expected to go. Then I create the post-blockchain processor, which will write to the last mock there. Then the gateway, which feeds as an output. So if you can see the output of the gateway feeds through to the processor. So there's no blockchain-y stuff. There's nothing in our framework actually active here. What we're doing is showing that fundamentally these components, the business logic works without a framework involved. And then I feed a message into it. I feed the expected message into it, sorry. And then say, after that, I put the actual message into the gateway. So that'll go through the gateway, through the post-blockchain processor, and then finally out to the hello world mock output, which would, in a real system, go back to the client. And I can show that it will step all the way through this. And if there's a bug in my code, it will blow up, throw an exception. If I want to debug it, I can step into the code. There's no threads involved. There's no server to run up to attach a debugger to. I can just do that straight from my IDE, just by hitting run or debug and creating a breakpoint. So I don't need to worry about any kind of... So there's no framework involved in this code at all. The only framework here is EasyMock. But that's entirely down to you as to what is your preferred mocker and how you want to do it. And in fact, you can write this without using any mocker. You can just create... you can do the mocking yourself. Now, if you don't want to write large unit tests like this, and certainly once you get to more complex examples, writing more and more code and keeping track of what is the essential logic of what's going on here gets harder. So most of the tests we actually do are data-driven tests. And this is what a data-driven test would look like. So in the first test, I'm sending a text message. And the source, I've got a source address. The event time would be set by the framework. It's the time the message is actually sent. So at the moment, it's 0 for the testing purposes. And you can see that in the very first message, I haven't set the text, or it's null. So I expect that to blow up. And then I send another message. Now it has some text on it. So this is the inputs. This is an input YAML file. So this is what the output would look like. So you've got that the first one failed, that's your failed command failed event. You've got the reason why there was a problem, but you can also see that the second message succeeded and produced the output you wanted. And when you're creating lots of more increasingly complex examples, this can be very useful. One of the key uses is actually determining when something goes wrong or something breaks, what went wrong, and how easy is it to fix it. So in fact, I broke this test. I made it that the reason doesn't get set. Right, so I just broke the code so that it doesn't produce a reason. So the reason is null. And because it does a string comparison on the left-hand side, it's got the YAML file of what it expected to happen. On the right-hand side, it's got what actually happened. And you can very quickly see where the discrepancy is. Now, if you're creating, if you're actually changing things like adding a field or this was an intentional change, you can quickly validate that, just copy the result and overwrite the expected outcome. You say, well, I'm going to treat this a bit more like a regression test and say, yeah, that change is reasonable. Now all I have to do is copy it into the output, and you can go through and correct hundreds of tests in an hour this way by just looking at, okay, the results, that's reasonable. I'll now go and correct that test so that the new outcome is the expected outcome. So, yeah, that's the finish of the presentation. Hopefully that was interesting.
Yeah, so you guys know, this is just a teaser for what's coming after the party, after the conference. The wine and networking, which is going to happen after the third speaker. Right now, I think we're ready for some questions for Peter. I'm sure you guys are quite exciting. Can we get some microphones there?
Okay. I haven't understand the consensus protocol that you're using. Can you explain that a bit?
Sure.
I mean, in more details, the details of the protocol, of the consensus protocol.
Sure. If I go back to this diagram here, so the consensus we're doing is something a bit like a 3-phase commit, would be one way of putting it, instead of just a 2-phase commit, where it goes through a number of stages, where it is more and more sure about what, not only what its state is, but what it believes is the state of every other node in the network. So the very first stage is very, well, the 0 stage is it sends out all the data it has, and it tries to send it to all the nodes that are available. That may or may not be successful. Then it attempts to gossip about what it knows and what it's seen to every other node, so that all the other nodes receive gossip about what everyone else has got a copy of. And then from that, they attempt to vote on which blocks, because every node can produce a block in each round, which blocks will actually get included. And the reason why they're not necessarily all going to get included is the node might be down, it might be too slow, it might have been sent to some nodes but not others. So then it may or may not include all of the blocks that are actually available. And lastly, what it attempts to do is say, well, if a majority of nodes all agree, that a block should be included from the different sources, then that block will actually get included. And at that point, it creates a voting, it says that this is a voting result. It includes all the messages that it based that decision on, and it's got the signatures of the voters. So any other node can look at that and confirm that yes, a majority of nodes did vote the same way and voted to include those blocks.
And who exactly produces the next block?
They all produce a block in each round.
So, okay, they produce they produce blocks, but who exactly is committing the blocks in the blockchain? Because that's the problem with the consensus, to decide which block is next in the blockchain.
Yes, so they all produce a block, and then the question is, what is the order of those blocks? Yes. Rather than which node, and none of them are a master. So one of the things that's different from proof of stake is that in proof of stake, one node is chosen to make that decision. Now, if that node then dies or that node is fraudulent in some way, you're trusting that node in that moment to make the right choices. However, in this system, they all run concurrently. They all make that decision. A majority of them have to come to the same conclusion. So if any one node is misbehaving or fails for any reason, it has no impact on the way the consensus is achieved.
But if you're producing 2 blocks, okay,
yes,
2 blocks at the same time.
Yep.
Each block independently is correct, but together they are incorrect. You could have double spending, for example.
Yes. So then what happens is then after you've included which nodes, after you've decided which blocks will be included in each round, you have to order them within a round. Now, there's a number of ways you could do that. At the moment, we just look at the signatures. We sort them by signature. Lowest signatures always go first. That's a somewhat arbitrary choice. It may be slightly flawed, but it doesn't really matter too much. As long as they all agree, once they've agreed, these 10 blocks will be in the next round from these 10 nodes, one each. They all come to the same. They all use the same algorithm as to how they should be sorted. Then all those blocks will be replayed in the same order. So let's take the example that some client connects in and very quickly sends to every one of the nodes the same transaction, or tries to send money out of their account in 10 different directions, right? So they got $1,000. They try and transfer out $1,000 10 times, right? So you get double spend. So what happens there? Well, what will happen is that if all of those nodes get a block that get included, they will then become ordered, and then this is where the post-blockchain processor will look at that message and say, based on that account's accumulated balance, does this succeed or not? And it will be the order in which those transactions completed as to which ones succeed and which ones don't. So the double spend is prevented by the post-blockchain processor. It says, what is the outcome of each transaction? The outcome will either be success or failure. It could be an application error. It depends on the transaction as to what all the possible outcomes are. And indeed, whether the order even matters. So in my Hello World example, the order doesn't matter. It will be the same order in every node, but in reality, if the order was changed, the impact of that probably isn't anything. But certainly for the payments, for example, the order matters, in which case the post-blockchain processor will say the first transaction succeeds, and every subsequent transaction will say there wasn't enough balance.
And the post-blockchain processor, where does this part execute?
It runs on every node. So every node does the same work.
The way I see is that this algorithm would only work if the nodes are trusted.
No.
Does it work if they are like wild west there? Like
they could all be doing different things. And what will happen is that if you connected to all those nodes, they will potentially claim different outcomes. But that's an issue that you could have anyway.
Okay, you have different outcomes, and then you have the algorithm of choosing the longest chain as the chain you
only if they all agree that the longest chain is the way to do it. So say, for example, you connect to a Bitcoin server, and it should be longest chain, but this server doesn't take longest chain. It just takes its own transactions all the time. And if you believe everything it says, then it's just going to run, and you're going to think transactions went through which didn't. So if you connect to one server and you trust it, it will tell you lies anyway, right? You haven't necessarily achieved anything. What this does is if you connect to 3 servers at random, one of them is misbehaving, and 2 of them are not, you will see that there's an inconsistency, and you'll be able to determine by talking to any other servers which ones really did work, even if one of them is lying and producing invalid results.
So you're saying the protocol works very well in untrusted nodes or no?
That's its intent, yes, is to work on a public blockchain, not just private ones.
Do you have a security analysis, like strong security analysis for this protocol? Like
we have had some security advice. We have a security advisor, and they've done some advice. They've not reviewed the protocol as such, but they've reviewed elements of how the system works.
Okay.
Maybe we can take some questions from the back, and we'll get back to your video.
Actually, it was close on the same topic. So I was wondering, how can you trust the majority, given that the entire blockchain is very efficient and you only need a few nodes to run it? It would be easy for an attacker to match the same number of nodes or even bring more, and so they would get majority on the network. And since there is no incentive, like mining, for external people to join the network, how are you going to handle this?
The intent is to support mining, but if you're running your own blockchain solution, you can decide whether mining exists or not. So it depends on how you accept nodes into the network. So in a more commercial environment, you wouldn't just allow anyone on the internet to run up nodes against it. You would need, so for example, if you use proof of stake, anyone running a node has to offer up enough stake to be at risk, and that limits the options as to who can run it immediately. Because, so say for example, Ethereum they require a stake of say $300,000. Not everyone's going to have $300,000 to be able to run a node in a proof of stake model.
Right, but this would guarantee that an attacker won't be able to have the resources to get the majority in the network. Right?
Correct.
Because they're not just cheap servers.
Sorry?
Because they're not just cheap servers.
Not from a commercial point of view. The machines themselves will be small compared to the stake that's involved. But that's entirely in your control. If you're running the system, you decide how big the stake should be. You decide how nodes are selected. So because we're using a weekly cycle, in the previous week, the accounts that want to run a node have to successfully hold up their stake. They have to put forward a stake, and that has to successfully be transacted and proven that that account can offer that, whatever the stake is. And then based on those nodes, the AI is also making decisions about, well, how should the chains be divided? Should a node be accepted? Has a particular node been proven to be untrustworthy? How old is the account? If the account has just been created yesterday, maybe that shouldn't be accepted. Maybe it needs to exist for a period of time before they should be allowed to run a node. Is there diversity in the nodes? This is where, for example, in a commercial environment, a new participant joins. You know the company, you may not trust them completely, but you know who they are, and you can say that they're only allowed to run one node, right? Then they can't achieve a majority because they've only been allowed to run a single node as a part of the network, for example. So you have some control over who can join the cluster in advance, either by stake or some sort of basic relationship with the organization running it or the individual running it. You can limit who can join, and that way no individual can achieve not just 51%, but you don't want to allow any individual organization to have more than a third, because if you achieve a third, you can prevent the cluster from working just by being malicious.
Okay, and about the AI who controls volatility, that's also some sort of centralized trust, because if that misbehaves or maybe it does something else that it's showing on the metrics.
Yes. So the AI is intended to be run by every node as well, so concurrently. So, and because the source would be available and the decisions it makes would be so either available internally or on a public network, publicly available.
So you'll be running it blockchain-like, like a smart contract that can be audited.
Yeah, it's a part of the blockchain.
Not only the code, but what it does.
Part of the blockchain service itself. It's not an additional centralized service as such.
Okay.
So again, you run into the situation, what if different versions of the AI or people change the AI in such a way that they're not trying to do the same thing? How would the AI attempting to do different things on different nodes work? I think that would depend on the inconsistencies they cause. So.
Cool, thank you.
So one of the things that we're doing, which is kind of different, is that rather than rely on any one node for anything, every piece of functionality is run on all the nodes simultaneously, which does sound less efficient. However, the intent is to make what they do very efficient. So for example, the post-blockchain processor is single-threaded. So there's only one core being used up. So even though you might have 100 nodes, you're actually only using 100 CPUs. The AI itself shouldn't be running very much. It shouldn't be making regular decisions all the time. So the cost of the AI running across every node in the cluster shouldn't be significant from a power consumption point of view, for example. It's more of an issue if the AI starts to become wildly inconsistent in terms of what every node is trying to do.
Sorry if I didn't understand this, but how do you recreate the balance of a wallet?
You take the snapshot from the previous week, and then you roll forward every transaction that occurred in that week. And at the end, another snapshot is produced, which becomes the basis of the next week's processing.
Thank you.
Which also means you don't need to retain more than a week's worth of data. So you have the opportunity to be forgotten. Obviously, just trusting the last week's processing might be a bit too much trusting, but you would be able to go back many weeks, check all of those transactions are correct, and you can go back as many weeks as you need to or would like to.
But in the financial system, don't you need to keep audits about every transaction?
True. So this is where it is in competition with GDPR. So for tax purposes, for example, you need to keep records for a certain amount of time. However, if there's no regulatory requirement to keep information, GDPR requires that you have the option to have it removed. So it kind of falls off a cliff. It goes from being essential to being undesirable at a certain point in time.
And one more thing. Can you write smart contracts on this blockchain?
Okay, so it depends on what you mean by a smart contract. The settlement of the contracts are done on the blockchain itself. However, to have a developer specified contract, you have to write Java code. Unlike some transactions where you can do it, it has its own meta language, its own VM for creating the contracts. There's different pluses and minuses, and from our point of view, we prefer each contract to be really simple and be super efficient and thoroughly tested. So then what happens if you want to be innovative and create a new transaction type? Well, each subchain can have different transaction types. They don't have to all have the same transaction types. You can create a subchain that for your purposes has a transaction type that none of the others understand or honor. That's fine. It's only the inter-chain transactions that everyone needs to agree on what they do.
Okay, and do you support multi-signature wallets?
Not explicitly. I mean, it's possible in theory. We don't have an implementation that shows that.
Okay, thank you.
First question would be, on these periodic snapshots, is there also a consensus between nodes similar to the voting?
There could be at the moment there isn't any kind of reconciler, but it wouldn't be too hard to add one. So for example, instead, when a node comes up, instead of going to one other node and getting a snapshot from the previous week, you could actually look at all the snapshots from all the previous nodes and then reconcile them. But it doesn't actually do that at the moment. It just, as soon as it finds a node that's got the data it needs, it just trusts it, which may or may not be legitimate. If it's running from one node week to the next, that's not necessarily a problem. It's only if you're a new node coming up, who do you trust? You may have accidentally trusted the node that was fraudulent in the previous week. And one way around that would be to actually get the same data from all the nodes and then make your own decision as to what the majority conclusion was.
So therefore reduce inconsistencies. Okay, and the second one would be on this AI. To mitigate volatility, would it use up reserve of coins? Or
I'm sorry, it's a bit...
Okay, so for this AI, would it, to mitigate volatility, would it use up reserve of cash or coins? And if so, in a flash crash, for example, in a public blockchain, would it be able to be consumed up?
Yes, in fact, it depends on how we want to handle it, but at the moment what it does is it will only spend 1% of its reserve in a week, which gets diminishing over time. So it's not actually able to prevent a flash crash. What it's more likely to prevent is where different bots, when there's very low volume, are able to manipulate the market on a low volume situation. So that's the main thing I think we can prevent. But if there's a flash crash, like a big sell-off or a big buy-up, the movement can still be more than the AI can allow because it can't exhaust its reserves. Otherwise, if it has no reserves, it's useless. It doesn't do anything.
Okay, thank you.
We have another question here in the front, actually 3 of them.
Regarding the smart contract support, so you're saying that the smart contracts would be written in Java and they will run on all the nodes, right? So
all the nodes in the same chain.
Same as Ethereum does with their smart contracts, right? So.
Yeah, so the difference there is that Ethereum allows you to create arbitrary contracts without changing any code in the system itself. Which is quite powerful, but it's near impossible to test because you run into the halting problem. You can't possibly test every combination in every path because the halting problem says that you cannot prove for any given arbitrary piece of code whether it will stop, let alone whether it has a bug in it or not. A good example of that is the Meltdown Spectre bug, which was only made public quite recently. That was a bug that was around for 20 years in nearly every CPU cache of Intel, AMD, and ARM for nearly 20 years, and it was only really picked up about a year ago. So for a very long, even though it wasn't discovered for well over a decade, it was still there, right? And that's with an incredible amount of use case and scrutiny and research effort available. It still wasn't picked up. So being able to determine that there is no bug in an arbitrary smart contract is very hard. There was one estimate from, I think it was Ernst & Young, that 10% of all currency has been hacked since they were created. And one way to avoid that is to only have very simple contracts that are very well understood and thoroughly tested. And they're the only contracts you can have. However, we've got the option to add contracts, particularly on subchains. And then we've got isolation between subchains. So if a particular subchain runs into a bug or it itself gets compromised, it doesn't impact any other subchain.
Okay, the problems with the smart contracts in Ethereum are due to the fact that the language is too powerful. You need, you don't want a Turing-complete language.
Yes.
This is why I was thinking if you allow random Java code to run on your nodes, that's a major security issue.
Yes, that is. So that's why you wouldn't do that. What you instead do is you would have, you can run arbitrary Java code, but the actual deployment on any individual node is up to the people running those nodes as whether they accept that transaction type or not with that code and that version. So that requires a bit of coordination between the individuals running that cluster, that subchain. If you can't get that coordination, you could run it on a completely separate subchain, for example, where maybe you run all the nodes. But even in that case, you can only compromise those nodes to the degree that that subchain has a balance for. So each subchain has its own balance. You can only transfer out of a subchain as much money as ever has been transferred into it. Right? So if you run your own subchain and it gets compromised or you try and manipulate it, you cannot influence the market any more than that subchain is worth.
Yes, but even influencing the subchain in an area which is very active, like, I don't know, the subchain for New York.
Yes.
Or something, that's a huge
That's potentially a huge amount. So that's where adding custom transactions would probably be more difficult because they'd be much more conservative about what is allowed. But if you want to be able to support smart contracts, for example, you could have a subchain just for smart contracts. Then the problem of deploying it and upgrading it and any kind of bugs is limited to just that subchain. It's not necessarily something that's going to leak across the entire system.
How about if you will have, for instance, just a domain-specific language, a DSL that will run?
That's right. So
instead of having the full, I think that's what you're saying, right?
So
this is what others do. So other like Archain or Cardano, they have their own, they develop their own language and their own virtual machine to support the language to limit the security issues, basically.
Yes, but if it's Turing complete, then it's actually, it's not possible to exhaustively test.
It must not be Turing complete, that's for sure.
Yes,
okay.
yes. So we've gone to the other extreme and said, if you want that functionality, you have to run it in a subchain. Then that's isolated to that subchain. And then it can do an OCaml or some of the subchains, we haven't worked out the exact details, but some of the subchains could be actually an Ethereum chain. Some of the subchains could be actually proxies for Bitcoin or any of the existing coins. It doesn't have to be running our coin. It has its, because once it goes, money is transferred in or out of it, it can be just a gateway to another completely different tech.
So basically you're saying you could wrap an existing, to have a gateway towards an existing chain and...
Just treat it as a subchain. Yes.
Yeah, nice.
And then you're able to do whatever you like with it.
One more thing, you said some code was written in Java, but a lot of code written in assembly and...
By CPU, not by volume. So the assembly code comes from the NaCl library, which is an encryption, US encryption library.
Okay.
And the authors of the encryption wrote an assembly version in x86, x64, and in C. And when the library starts up, it works out which one's the fastest and just uses that. And we didn't write that. It's part of a standard library called libsodium. And then we just have a wrapper around libsodium called Chronicle Sol that just calls those libraries natively. And it does all the sort of heavy lifting from a CPU point of view. But from the volume of code, in our case, it's minimal. Even the assembly is actually minimal in the amount of, I think it's something like 50, 60 lines of assembly. It's not really a lot, but in terms of where is the CPU burnt, that's actually where most of it goes. So I guess I'm just making the point that if it wasn't written in Java and it was written in C or assembly, you're only going to save less than 10% of the CPU used anyway, because most of it's already written for you, either in the OS or in assembly.
Okay, thank you.
We have probably the last question for this session.
Hi. How many nodes are at the present moment in the network that are composing and running the network? And the second question about the voting process, if you could elaborate it a little. The rules, for instance, is it secret or there are some guiding principles there?
Yes, so at the moment, because it's just under development, the most we've run it on is 3. So it's not a lot, but that's because it's just under development at the moment. In terms of how does the voting actually work, what we've focused much more is trying to make sure we have the right structure so that the actual way voting works doesn't matter so much. So from a very simplistic point of view, the open source version, all it does is last one wins. That's the voting structure, right? Very easy to bias if you did it deliberately. But we find that even with last one wins, it gets consensus almost all the time, because one node is consistently seen as slowest by all the others. Right? Now, what we're looking to do is to develop smarter algorithms that don't allow any one node to deliberately bias the outcome. So it may be done by median result rather than last one. Or we've got a number of different strategies that we could look to see whether that improves the outcome, but really what we've focused on is making sure that we believe the structure is right, so that if we change the voting structure, we change how the gossiping is fed into the voting as well, then we don't need to change anything in, like, for example, the code you saw or the architecture. None of that has to change. We can just say, well, this is a smarter way of using the information from gossiping to decide what to vote on.
Thank you.
Okay, thanks a lot, Peter, for the amazing presentation and insights. And thank you all for all the questions. You really made my life easier today, not having to pitch in so much. So I owe you probably a glass of wine. We're going to have a break for like an hour, and we're going to meet at 2:30 here for the third and last session for today. And I'm sure, knowing Peter, he's not going to be too upset if you stumble upon him on the entrance and ask him more questions. Okay?
Yes.
Thank you, and enjoy the lunch.